In this video, I will discuss the presence of errors in numerical solutions and talk about different kinds of errors and their origin. As we already said, numerical solutions can be very accurate, but are almost never exact. So this means that if we compute the difference between the true solution x subscript ts and the numerical solution x subscript ns, we will almost always get a non-zero error or a total error, which we will denote as E. Now this total error, it consists of two main parts. One part based on round-off error or rounding error, which is related to the way in which computers store numbers and perform operations with them. Now, rounding errors were already introduced in the previous video where we discussed exactly how numbers are stored as floating point numbers in the IEEE standard in computers. So that is one part of the total error. And in addition to this round-off error, we also have a truncation error. Now, truncation errors, they have quite a different origin, and they are due to the approximative nature of most numerical methods in practice. And we will go into an example a bit later. Now, a simple example is if you try to calculate the sign of pi in MATLAB. And well, we can see if we type pi, MATLAB will say, well, I think pi is this. And then if we compute the sign of pi, which analytically would be exactly 0, we get an answer which, although it is very small, so this is 1.2 times 10 to the power minus 16, so this is a very small number, it's not exactly equal to 0. So in this case, we know the true solution, which is 0, and we see that the numerical solution is 1.2 times 10 to the power minus 16, so the total error is equal to this. Now, how did this happen? Well, let's take a look. So first off, we clearly have a rounding error here. So if we ask MATLAB what pi is, it tells us a relatively accurate representation of the number pi. However, we know pi is an irrational number and it has an infinite amount of digits after the decimal point. So it clearly is not equal to what MATLAB is saying here. So it has much more digits after this 9. So for instance, 3, 2, etc. are not accounted for by MATLAB here. Also, the way MATLAB is calculating the sign function is a source of error. And that is, as we will see in one of the next slides, that will be a truncation error because this is because of the way MATLAB approximates the sign function. So here we clearly have these two different sources of error, which leads to the fact that MATLAB seems to think that the sign of pi is not exactly equal to 0. First off, let's take a brief review of round-off errors, which were already discussed in the previous video on the numerical representation of numbers within computers. And the origin of round-off errors is that we only have a finite amount of bits available in storing these numbers in the memory of a computer. Now, if the amount of bits necessary to represent the mantissa in binary format is larger than the amount of bits which are available for storing the number in the computer, well, then there's nothing else to do but round the mantissa such that it is such that the stored number is close to the actual mantissa, even though it cannot be equal. So examples for when this is the case is, for instance, for all irrational numbers. Because no matter what representation you use for an irrational number, be it base 10, be it base 2, it always has an infinite amount of digits after the decimal point. You can never get an exact decimal or binary representation for any possible irrational number. So in our previous example, we could have already, if we thought this through a bit more, we could have already guessed that the number pi could never be represented exactly in a computer with a finite amount of bits available for storage of numbers. But even rational numbers, which look a lot less, uh, well, let's say rational numbers which look a lot more friendly, can have no exact binary representation. For instance, this number 0.1, for which we've shown in the previous video that the binary representation would require an infinite amount of bits. And this is actually also the case for numbers like 1 over 5, 1 over 3, 1 over 7, etc. But even rational numbers for which we can get an exact binary representation, but which features a very large mantissa, a very long mantissa, for example, using 60 bits, they would also need to be rounded in order to store them in a double precision IEEE floating point number. So also there rounding errors would occur. So all these conditions, well, there's a lot of numbers which cannot exactly be represented in the computer, which means that almost always you will have to deal with rounding errors. An example here, again, this number 1 over 10, which in decimal is simply 0.1, which in double precision floating points, well, would have this, I'm not going to read it out loud, but would have this representation. So that's the IEEE floating point representation, where we have the sign, the exponent, and the mantissa. Now converting this back to decimal would lead us to this number. So this is actually the closest that a computer can get to the number 0.1, which means that the rounding error for the number 0.1 is 5.55 times 10 to the power minus 18. So whenever your computer tells you that the outcome is 0.1, it's actually lying. The computer always thinks 0.1 is 0.10000, etc. 555. There is no such thing as 0.1 for a computer that uses IEEE floating point standards. Now, in general, as we've also seen in this previous slide, rounding errors are quite small because we use quite a lot of bits for storing these numbers. However, they can accumulate in sequences of calculation. So if we do repeated calculation in which every time we add some kind of rounding error, then they tend to accumulate, and after a while they can become quite noticeable. And also there are situations in which they become much more apparent. For instance, when we use numbers with a significant difference in magnitude, or we subtract nearly identical numbers. So an example here is if you type this up in MATLAB, if we declare the number a as 10 to the power 23, the number b as 0.01, and we try to compute a plus b minus a, well, MATLAB follows the order of operations from left to right. So then it will declare, it will say that a plus b, well, it will round that to a and subtract a from it, which leads to 0. If we scramble up this order of operations and we say a minus a plus b, which in standard mathematics is something you can absolutely do, that's simple commutativity of the addition and subtraction. So just switching around the order of operations in addition and subtraction is something you can completely do. But we see that, well, if we switch the order of operations, we get a different answer here, which can be very odd for people that don't know anything about numerical mathematics and computational science. Obviously, after having viewed this video, next time you encounter something like this, you will not be surprised, but you will be able to explain this kind of behavior. So this is very important to keep in the back of your mind when you're dealing with very large numbers on one hand and very small numbers on the other. Rounding errors are always right around the corner in that case. Let's consider this example over here. So we have this function where f of x is x times square root of x minus square root of x minus 1. If we enter this into MATLAB, well, we can do this like this. We compute this for x is equal to 10, x is equal to 1000, and x is equal to 10,000. And well, this has quite high precision. So this has a 64-bit double precision, and this will give us these answers over here. Now let's compute these things manually using only 6 digits decimal computation. So 6 significant digits in our computation. And well, for small numbers, everything will work out fine. So we see that if we substitute x is 10, we get 10 times the square root of 10 minus the square root of 9 is equal to this. And this is equal to, so here we round it to 6 significant digits for the square root of 10, which is obviously, we make some small rounding error here. But we see that in the end, if we compute this, well, this number is equal to the full precision number, but rounded to fewer digits. So that's fine. If we repeat this for 1000, well, again, computing the square root of 1000, we round here to 6 significant digits. Also here, we use 6 significant digits, and this leads us to 15.8, which also is very close to the rounded version of the full precision computation of this function. However, problems start to occur when we put even larger numbers in there. Why is this the case? Well, if we substitute x is 100,000 in here, well, then the square root of 100,000 rounded is 316.228, whereas the square root of 99,999 is 316.226. So this actually tells us, well, these two numbers are quite close to each other. For large x, square root of x and square root of x minus 1 get closer and closer to each other. Now, after rounding, well, we rounded this to 6 significant digits. Well, if we compute this, we end up with 200. Now, 200 is very far from the actual full precision computation over here. So the rounding errors that we made when computing this number and this number, they completely destroyed the accuracy of our final output. And this is because we subtracted two numbers, two large numbers, which are very close to each other. We can try to avoid this by massaging our initial analytical expression. So for example, if we multiply this with this square root of x plus square root of x minus 1, well, after some algebraic manipulation, you can see that these two are equivalent. So in simple continuous mathematics, standard mathematics, these two statements are completely the same. But we will see that if we use finite precision computations, here we get rid of this subtraction of two large numbers from each other, which is very beneficial for the accuracy of our computations. So let's take a look. If we substitute 10 into f, well, again, this yields a very satisfactory accuracy. 1.6228 is very close. Well, it's basically the rounded version of this full precision number. For x is equal to 1000, Well, similarly, 15.8 is basically this rounded. And whereas in the previous case we made a big mistake when x was larger, here we avoid subtracting these two from each other, but we just add them. And we see that the final outcome, even though we have rounding errors over here, that the final outcome is simply equal, well, at least the first 6 significant digits are simply equal to the full precision computation. So we were able to get rid of this amplification of rounding errors by avoiding the subtraction of two large numbers from each other. And I suggest you do these computations by yourself, also with a piece of pencil and paper, as this will really show you how these rounding errors become bigger when you subtract these larger numbers. Moving on to truncation error. Well, the origin of truncation error is very different. It's because we're using non-exact mathematical procedures in these numerical methods. They are independent of rounding errors, and even if there were no rounding errors, truncation errors would still exist. So they depend only on the specific algorithm that we use for a certain task. The name truncation error actually originates from truncating a infinite sum or an infinite series to a finite sum or a finite series that we can actually compute and handle within a computational framework. An example of such a truncation error can be shown when trying to compute a sine function. Sine functions are difficult functions to compute. They are trigonometric functions for which no simple algebraic formula exists, so we should approximate them. And in order to compute them numerically, well, we should use a form which computers can easily do. Well, and computers can easily calculate polynomials, so x's and powers of x's. Now, the Taylor series expansion of the sine function, well, that allows us to compute an approximation for this trigonometric function using an infinite series. And if we use an infinite amount of terms, this would be an exact representation of this trigonometric function. If you don't know how such a Taylor series is constructed, I suggest you look into chapter 2. But we see here clearly that this has all odd powers of x, and this will keep going on until infinity. And looking at a specific example, let's say we want to compute the sine of pi over 2. Now we know from trigonometry that the sine of pi over 2 is simply equal to 1. Trying to use this Taylor series expansion to compute that sine, well, that's simply equal to substituting x is equal to pi over 2 into this Taylor series function here. So, and then we do this for a increasing amount of terms until we reach a desired accuracy. So the first term here would be simply x, where x is equal to pi over 2. And we see that this is equal to 1.5707. This is obviously not accurate enough for a good approximation for this sine function. So we have to start adding additional terms. Adding the second term over here, well, we see that we're getting closer, 0.92. And as we keep on adding terms, we get closer and closer to the real solution, 1.0. Now, obviously, in the practical case where x is not equal to pi over 2, but to some arbitrary value, we don't really know the true solution. And we can only compute this right-hand side over here. But in this case, we do know the true solution, which is 1. And we can exactly quantify that using 6 terms. This truncation error is 1 minus the approximation that we have over here is 5.62 times 10 to the power minus 8. Also, when approximating the derivative of a function, this truncation error comes into play. Let's say we want to compute the derivative of a function in a given point x1. Now what we would do then is construct a Taylor series around the point x1 using a second point x2. And more information on how this is actually done and how this computes or approximates the derivative in an accurate manner will be discussed in chapter 8. But again, you see that this is based on this Taylor series concept. So if you're not very familiar with it, I would suggest you read up on it. But we see that basically this leads to this kind of function over here. So we see that f at point x2 is equal to f at point x1 plus then a first term, which is the difference in x times the first derivative at point x1 plus a term proportional to the second derivative plus a term proportional to the third derivative, etc. And these terms tend to get smaller and smaller. Now we kind of recast this expression into an expression explicitly for this first derivative by some algebraic manipulation of this first expression. And this gives us then this first term plus minus a second term, which is proportionate to this second derivative plus a term which is proportional to the third derivative. And we see that if x1 and x2 are close to each other, that we hope that this is small. Now we approximate then this first derivative by just getting rid of all these terms, just keeping only the first term and dropping out all the rest. And this is what in chapter 8 we will call a finite difference approximation of the first derivative. So that's an approximate derivative, and then the truncation error are all the terms that we dropped here to the right. And we obviously hope that they will be small. Now, just as a quick teaser here, we can look at how this actually looks on a graph. And in this representation, the finite difference slope or the finite difference derivative would be the red line, whereas the actual derivative would be the purple line. More on that will come in chapter 8 on numerical differentiation. If we observe a certain total error, we need to be able to assess how problematic this error actually is in assessing the accuracy of our numerical solutions to our equations. And the answer is, well, this depends. So if we observe an error of 2.5 times 10 to the minus 8, this might seem as a small number to you. Well, this is definitely not problematic as an error if the true solution is of order 1, because then the error is much smaller than the solution, and we can indeed say, well, this is a small error. If on the other hand the true solution is of the order 10 to the power minus 7, well, in that case I would start having my doubts because the error is not much smaller than the solution itself. So this leads us to the definition of this concept of a relative error. And this relative error can be defined as the total error divided by the value of the true solution, if you have that value available. And we can see indeed that, well, in this first case, the relative error was very small. So 2.5 times 10 to the minus 8. So the relative error is very small. This is not a problem at all. However, in the second case, we see we have a relative error of 0.25, so that's an error of 25%, and we can start having our doubts on the accuracy of our numerical solution. So, rounding up this part on errors in numerical solutions, we discussed that the total error can be defined as the true solution minus the difference between the true solution and the numerical solution, and that this is kind of omnipresent in numerical simulation. So it will be very rare that you have a case where there is no difference in the true solution and the numerical solution. This total error consists typically of two main parts: a round-off error, which is due to the finite precision that we have when storing floating point numbers in computer memory on one hand, and on the other hand, the truncation error, which is dependent on the numerical method that you're using. Assessing the importance of such an error can be done using a relative error. So if you know the true solution, you can normalize this total error with it, and based on that, you can assess how big this total error actually is in comparison to the true solution. Now, an important remark that has to be made is that in practice, this true solution is very rarely known. So the actual error, in practice, most of the time you have to estimate it instead of really being able to compute it. And that is also an important issue in assessing the quality of your numerical solutions.